If you have been watching my videos for some time, all these books might look familiar with you. If you learn vector analysis by reading this book alone, you will find vector analysis is very boring. Or if you learn electricity and magnetism with this book alone, you will find electromagnetic theory is very complex. However, if you read these two books simultaneously, you will find this book, Vector Analysis, is very useful and fun. At the same time, you will find electricity and magnetism is no longer as complex as it might look. My point is that if you read multiple books simultaneously, you can better understand both books, not only vector analysis, but also electricity and magnetism. Such reading is called cross-reference. In this book, Electricity and Magnetism, I'm moving pretty fast. Now, Chapter 8, Magnetism of Steady Current. If you scroll down, you can find Lorentz force. This book now introduces magnetic field. This force, Fm, is called magnetic force. So, magnetic force is proportional charge Q times V, velocity, cross magnetic field. If you scroll down, you can find electromagnetic force. This part, QE, forms electro force. Q times V cross V forms magnetic force. So, this equation 8.2 is called electromagnetic force. In this book, B field or magnetic induction or simply the B field is introduced for the first time. If we scroll down, we can find Lorentz force on the volume B is then given by volume integral J cross the B field or the magnetic field. This is integral form of Lorentz force. I haven't yet discussed current density. This J is called current density. If you scroll down, you can find some examples. Charged particle in a constant magnetic field. Now I want to know the source of B field. In chapter 8.3, the source of B field. If you scroll down, you can find these two formulas. The meanings of this formula, also this formula, is explained in this section. In case of magnetic B field, divergence of B is always 0. Curl of B is equal to or proportional to J. J is current density. This equation is called Ampere's law in derivative form. In this case, electric field is not yet introduced in this equation. In the section 8.4, you can find integral equations of magnetostatic and Ampere's law. So, this is Ampere's law in integral form. We will eventually move to Maxwell's equations in chapter 14. If you scroll down, you can find this formula. This formula is called continuity equation. To understand this continuity equation, we have to go back chapter 7, steady currents. I will film 1 or 2 more videos about the definition of electric current. In this part of the text, current density is defined. I will film one or two more videos about current density as explained in this part of the text. In this episode, I will explain the continuity equation, local conservation of charge. In my current session, I will explain equation 7.9. This equation is known continuity equation. I would highly recommend you to read this part of the book on your own. However, if my explanation is too complex or ununderstandable, then from vector analysis, chapter 6, Divergence theorem, Stokes theorem, and related integral theorems. In this section, if you scroll down in page 147, problem 6.28, a fluid of density rho moves with velocity v if there are no sources or sinks. Prove that this continuity function with j rho times v. If you have watched one of my previous videos, this rho v should look familiar with you. In our previous video, I explained rho as density of mass. Now, in this episode, this rho will be charge density. This book explains the continuity equation. If you still fail to understand this continuity equation, then from Thomas's calculus, early transcendentals. In this book, last chapter, chapter 16, integrals and vector fields. In this chapter, last section, the divergence theorem and a unified theory. In this section, if you scroll down, you can find continuity equation of hydrodynamics. Today is March 5th, 2023. This is my 11th episode for C++ Electricity and Magnetism with vector calculus, classical physics. In this episode, I will discuss current density J and continuity equation 2. I filmed this video for my own reference later, not for my audience. If you scroll down, you can find my previous video, episode 8, Flux density, divergence, Gauss Law. We will watch this video to review what flux density, divergence theorem means. After watching this video, my current session continues. Select empty space, click this button, 008, Gauss Law. Click this button, gauss.cpp, hit enter. I will close this document, Ctrl V. I will drag and drop. Calculus by James Stewart, 9th edition. Click this button, Chapter 16, 16.7, surface integrals. If you scroll down in page 1188, you can find surface integrals of vector field flux. We will start with flux. I will explain Gauss' law from scratch, starting with flux. I will arrange side by side. We have to read our text very carefully. Suppose that S is an oriented surface with unit normal vector n. This unit normal vector S is a surface, and imagine a fluid with density rho and velocity field V flowing through S. So, a fluid is passing through this surface or flowing through this surface. N is normal vector to this surface. Think of S as an imaginary surface that doesn't impede the fluid flow like a fishing net across a stream. Then the rate of flow per unit area is given by the vector field rho v. Vector field F is given rho v. Then the rate of flow mass per unit time per unit area is given by the vector field rho v. We will start by defining volume. Volume is denoted delta V. It can be said that delta X times delta S. Delta S represent Sj in this figure 11. Delta S represent this surface patch Sj. So delta X can be height. Delta S can be base area of the volume. We now defined volume. Then density is denoted by symbol rho. Density equals mass over volume, or we can say delta M. Our volume is defined here. I will copy and paste here. So this is our density, mass over volume. From this, if we multiply delta X to rho, we have rho times delta X comes from here equals delta M, the mass is here, then delta S, the area. This equation holds. The velocity field V, this velocity field V can be defined equals the distance of the flow. Delta X is the distance of the flow over time, delta T. This is represented or denoted by the symbol V. This V is velocity field flowing through surface S. Now this part. Then the rate of flow mass per unit time per unit area is given by the vector field rho v. We will define rate of flow first. Rate of flow is defined mass per unit time, mass per unit time, or delta M, here delta T. We now defined rate of flow, mass over unit time, or delta M over delta T. Now the vector field rho v, vector field equals rho times v, rho v, the vector field rho v. Now let's see what it means. Rho is this value, so delta M here, delta X times delta S from density. This is rho, our density, times V. We defined velocity field V here. So delta X over delta T here. We cancel out delta X, delta X. If we cancel out delta X, then delta M here, delta T here, then times 1 over this delta S here. With this, we can say delta M over delta T. Delta M over delta T is this part. Then delta S here. In other words, delta M over delta T here, delta M over delta T is rate of flow. So this is rate of flow over delta S. This is rate of flow over unit area. This rate of flow unit area. Unit area means delta S. Now we understand what is vector field. Vector field is defined to be density times velocity. Velocity field in this equation, delta x stands for the distance of flow. I will read this part once again. Then the rate of flow, mass per unit time per unit area is given by vector field rho v. Vector field rho v is a rate of flow over unit area. Now we define flux of F across S. If F is a continuous vector field defined on an oriented surface S with unit normal vector n, then the surface integral of F over S is given with this equation. This integral is also called flux of F across S. Now here we define flux of F across S is defined surface integral F dot ds. This equation comes from here. In this equation, flux of F across S is F dot ds surface integral. F is a vector field defined to be rho times v, density times velocity. Gauss's divergence theorem says that flux surface integral equals divergence volume integral. I explained many times about this equation, so I will not explain about this identity. Instead, we will learn what this flux surface integral means. Now, I will close this document. Instead, open Thomas's Calculus. From this book, Thomas's Calculus, Early Transcendentals. Click this button, scroll down to the last chapter, last section. Now, I will close it. Chapter 16.8, the Divergence Theorem and a Unified Theory. In this page, divergence in 3 dimensions. The divergence of a vector field F is a scalar function. Divergence F or del dot F. Divergence F has the same physical interpretation in 3 dimensions that it does in 2. If F is the velocity field of a flowing gas, the value of divergence F at a point xyz is the rate at which the gas is compressing or expanding at xyz. The divergence is the flux per unit volume or flux density at the point. The divergence is the flux per unit volume or flux density at the point. Now, I will arrange side by side. Here, I will copy this part, then an indent. From this equation, vector field F is defined rho times b. So, rho times b. From this, copy, paste. This rho times b is defined delta m over t delta s. So, this part can be delta m over delta t times delta s, like this. Now, delta s ds cancels out. Then it becomes delta m over delta t, like this. From this, we can say delta m for total mass over time passing through surface S. So this is our conclusion, or flux of F across S is total mass passing through the surface S per unit time. Flux of F across S is total mass passing through the surface S per unit time. Now you understand what is flux. This is total mass delta M over delta T. Please compare flux of F across S with the rate of flow. In case of rate of flow, surface is not assumed. In case of flux of F across S, the surface is assumed. That is the difference. Now I will read this part once again. Divergence F has the same physical interpretation in 3 dimensions that it does in 2 dimensions. If F is the velocity field of a flowing gas, the value of F, the value of divergence F at point xyz, is the rate at which the gas is compressing or expanding at xyz. The divergence is the flux per unit volume or flux density at the point. Once again, the divergence is the flux per unit volume or flux density at the point. So we will start from here. Once again, I copy and paste it. Now this is this equation. Copy, paste like this. We got this result from here or through here. Then this part I will copy and paste. From here we will multiply volume. We defined volume like this. Delta x times delta s. Copy, paste. We will also divide like this, like this. So I multiplied the volume on left hand side, on the right hand side. Now we take limit. The volume, I say V approaches 0. I will replace like this. So volume is approaching 0. Limit V approach 0 like this. Now let's pay attention to this part. Left hand side becomes dm over dt times dv equals this volume cancels out. Then we have, I will arrange like this. Now dm over dv, scroll up, mass delta m, this is delta v. So delta m over delta v is a mass density. So I can say density here over dt equals divergence F. Now let's go back to this equation. In this equation, from flux of F across F. In this equation is total mass M over delta T. Then we divide it with volume like this. So this is flux over volume. This is on the right hand side. By cancelling dV with delta V, we got divergence F. So divergence F is called flux over volume or flux density. At the beginning of current session, I said we will learn what is flux. What is flux density? Flux means total mass flowing through a surface S. Flux density is flux over volume or flux density. Open up Visual Studio Code, Electricity and Magnetism. Select empty space. Click this button. 011. Continuity. Click this button. Cont.cpp. Hit enter. Ctrl V. I will close welcome window. Now I will drag and drop vector analysis. Chapter 6. Divergence theorem, Stokes theorem, and related integral theorems. If you scroll down, you can find problem 6.28. A fluid of density ρ moves with velocity if there are no sources or sinks. Prove that discontinuity equation where J equals ρ b. I will arrange like this. Of course, we are not interested a fluid of density. We are interested a flow of charge density or electric current. In this equation, J equals ρ v. We will learn what is J. J is delta I over delta S, or electric current over unit area. So delta I represents electric current that is passing through unit area delta S, or electric current I is delta Q electric charge over delta T, the time, over surface area. So we can say delta I is delta Q over delta T times delta S. I will give a line break here. Our charge delta Q moves delta X distance in delta T second. We multiplied the distance delta X in the numerator. So we should also multiply delta X in the denominator. Now we rearrange like this. Delta S times delta X, delta T here. Then like this. We rearrange it. This expression like this. Now I copy, paste it. This is our volume. Delta X over delta T is now velocity. V represent delta X over delta T, the velocity of our charge movement. Delta S is surface or area. Delta X is distance our charge Q moved in delta T. Delta S times delta X is volume. This represents volume. So it becomes ρ, the density of a charge, times velocity. It means J is electric current over unit area, or current density. This current density is equal to ρ times V, where ρ is defined delta Q over delta V, or charge over unit volume. It is called charge density, where J equals ρ V. J is current density. It is ρ times velocity. This velocity represents the velocity of our charge movement in time delta T. Now, from charge density equation, we can copy delta Q equals rho dV here. We rearrange it. Charge density expression like this. Now we take volume integral like this. Then left hand side is total charge Q when the density of charge is rho. This expression is this expression. We can say dV. In this book, M represents mass of a fluid. In our example, Q is charge, that is, in the volume V. Now, 1. The time rate of increase of this charge Q is, we have to take derivative from this equation. So, derivative of Q with respect to T equals round over round T. This can be written volume integral round rho over round T dV round Q over round T represent time rate of increase of this charge Q. Please observe that round Q over round T or delta Q over delta T. This is electric current. Also note that the time rate of this charge. The time rate of this charge means electric current. Increase means current increase. Increase means time rate of this charge Q in the volume V enclosed by the surface S. That is, inside the surface S, the time rate of this charge Q is increasing inside this surface S. Also note that J is defined electric current over unit area. From this, we can rewrite this equation like this. J times delta S equals delta I. If we take surface integral, it becomes ds di or I equals surface integral j dot ds. Here I will copy this, paste it here. J is rho times V. I will substitute rho times V for J. This is scalar multiplication. This is vector multiplication. Now I will scroll it up. Here, 2. The rate of charge leaving volume V is surface integral rho V dot ds, where ds is surface differential outward normal. Because ds is surface differential outward normal, the rate of charge leaving volume V is decreasing. That means the time rate of increase of the charge is it should be negative, like this. The rate of charge leaving volume V is surface integral rho V dot ds. We learned in our previous video. This is the flux flowing through the surface S out of our volume. So it is decreasing. By putting negative, it becomes the time rate of increase of the charge. It can be written by using J. The current density is rho V. So instead of rho V, we can use J here. Now, by applying Gauss's divergence theorem, we can say divergence of J dV, volume integral. Now, 3. This is the rate of increase of the charge in the volume. So, we equate this increase. This increase should match with this increase. So we can say, I will copy this, paste it here, round rho over round t, like this. Now I will copy this, paste it here. We will move left hand side to the right. It now becomes plus. Then I can arrange like this. So it should be 0 because we moved left hand side to the right hand side. With this, we can say volume integral round rho over round t plus divergence J dV. If this equation is to hold independent of xyz, what the volume, this integrand should be 0, or this should hold. This result is our continuity equation, or we can say divergence J plus round rho over round t equals 0.